Welcome back to the last lecture on modular logic design. So what I ended with yesterday is a diagram of how high-level logics are organized using the example of first-order logic and propositional logic. So we had propositional logic and then a theory of what the model of propositional logic needs, and that was itself written inside first-order logic. And here we declared things like proposition, and here we had things like booleans and if then else, and then we were able to give a morphism that translated propositional logic into this language to get the semantics. And in particular, the deduction operator was mapped to the property of being propositions were mapped to terms of TM pool, and proofs of F were mapped to the first order logic statement that F equal to the true Boolean, truth value 1. Remember, this stat and this stat are imported from the same place, but they're very different. This one from propositional logic, and this is the one that we're getting to meta language first. We can then extend this first order, in particular adding things like universe of terms. To be clear, this could now be the untyped version, and here we need the typed version. Then we can't quite use this theory to represent the semantics of first order logic, because we cannot define the semantics of the quantifiers using just if then else. Quantifiers need some kind of binding like operation. One easy way to do that is to go to higher order logic. There's a theory of the full model. So first order logic is included into high order logic in a relatively straightforward way. And then this is also a straightforward inclusion, where in addition to booleans and ifs and else, we have things like minimum, maximum, which we can use to take, say, the minimum of a set of truth values, which is exactly how we can interpret then the universal quantifier. So then that gives us, this a bit lower actually. Max, and then we can write down the first one. Now is a morphism into the simplest language in which we can express it. If we want the standard semantics from textbooks, we have to go even further, translate higher order logic to set of C set theory. Here we in particular do things like PP translates to set, meaning types are interpreted as sets. And PM translates to elements of the set. So every term of type A goes to an element of the set A in the set theorem. But here in particular, we need things like set, the elementhood operator, and the special constructor lm to get us the elements of a set. I want to talk about that maybe later if we have time. The theory of the full model in ZFC is basically just a single non-empty set. That's all we need. So we have to declare the universe to be a set that's going to be the universe of our full model. And then we can also continue the translation up here, mapping in particular the special type for the universe, which we need here to the set for the universe here, which works because types are map sets. Now, what I haven't given you many examples of yet is the individual theories of the logic. So let's look at an example where we might have theory of magma, say, extended to, well, let's see, very modest theory of semi-groups. So here we would just declare the binary operation on terms and we would extend it here with an axiom for associativity. It's like the hello world example of a stereomorphism in first order logic series. Magma semi-group, and of course you can then do the whole algebraic hierarchy and so on. More generally, every time in math you have a statement like every x is a y, you can try to capture it as a stereomorphism, formalizing x and y as series, and the proof that every x is a y as a stereomorphism from x to y. Sorry, from y to x. The models always go together there. I'll show that later. And we need a little bit more knowledge about the categorical properties of these operations. So far, all of this is happening in the category of LF theories and theory morphisms. So every point in this graph is an LF theory, like I have shown it before, and every edge is a morphism. I'm using double lines for the non-trivial ones and hook arrows for the trivial ones where we're just including another theory. So one important thing about this category is that it has push-outs. Do you know what a push-out is? Anybody? About half of you. So push-out you can think of as a union with sharing. You have two modules, M and M prime. You would take the union. So as a kind of think of an inheritance from both of them. You want to import two things. But maybe they already share something. Maybe they both include some L, and you don't want to duplicate the L, you just want one copy of the L. And maybe even if they don't share directly, maybe there is a variant of L already in here, and you just want to say, well, whatever this L stuff that comes from here, I want it replaced with the image of L here. So it's a typical operation that you get when you instantiate parameterized modules and merge them into one bigger module. And categorically speaking, that's exactly what the pushout does. So it takes these two, merges them under the provision that whatever comes from here is shared and doesn't give us two copies. Pushouts in general are difficult, but one very nice property of these categories of theories that we often construct is that they have pushouts along inclusions. Meaning if at least one of these two arrows appears in inclusion, we have a very, very easy construction of the pushout, which is basically just a homomorphic extension. So I will demonstrate that. Let's say we're going all the way. So let's say we bypass this one and immediately go to set theory, which is just the composition of these two morphisms. Then what we have is one long morphism from first order logic to its semantics in set theory. and we have an inclusion here. We can now do the push out, which would get us, give us a rectangle where the theory magma is mapped along this morphism, and that gives us a name. Let's call it just full SEM for the semantics of first logic. So we can take magma, translate it along full SEM, and get an inclusion down here, and the whole thing is a push-out rectangle. And we construct this push-out in an extremely straightforward way. All we have to do is start with this set theory plus non-empty set. Also, technically, we use an axiom of non-empty here, right? Non-empty is an axiom that U is not empty. So take the theory of a non-empty set, include it, and then we take everything that magma had, but translate it along the morphism. So instead of up term to term to term, we get up being an element of the universe, to element of the universe. So basically, we just take the declaration that magma adds to the logic and translate them along the morphism. Just replace all the names with whatever the morphism does. Or the axioms are translated accordingly. And we can do the same also for semigroup. Then we get here full SEM. Semigroup with the corresponding inclusion morphism. So this construction is functorial, meaning we can think of this morphism here as a functor that maps extensions of this theory to extensions of this theory. That's why we get these two, and because it's functorial, it also maps all the morphisms. So this morphism goes morphism here. So not only does it map morphism, but it preserves inclusions, meaning inclusions get mapped to inclusions. But more generally, any diagram of formalization that we build down here, with whatever non-trivial morphisms we have constructed, immediately becomes a corresponding diagram here of a set theory. Now the relevance of this construction is for the representation of individual models. So far, I've only shown you how to represent the collection of all models, like an abstract model. This theory represents an abstract model of first-order logic, written in set theory without any functional predicate symbols, like for the empty theory. All we need is a non-empty set. But in practice, of course, we want models of specific theories, like the theory of magma or the theory of semigroups. So these theories here do exactly that. They represent what a magma is or what a semigroup is, but now in the language of set theory. So we have taken the syntax language that we had, translated into a semantic language, but the essence is still the same. So now here we have the representation of what a magma is in set theory. And indeed, this has undefined symbols for the non-empty set, for the proof that that set is in fact non-empty, and for the operation on the elements. That's exactly what we need to give a magma. A set, proof that it's non-empty, and the operation. Similarly, if we want a semigroup, we have to additionally prove it's associative. So we have the associativity axiom here, along with the translated specification that if we evaluate the formula for the associativity axiom in here, we get the truth value 1. Didn't actually draw the translation of the truth values. Where does that go? We're in here for the big morphism. We have that propositions go to elements of the set 0, 1 for the truth values in set 0. So somewhere in here we can define 0, 1 in the usual way in ZFC sense. So now we can use an individual morphism that goes here to represent all models. So this would be any individual magma looks like a morphism like this. And it has to be a morphism from set of C extended to non-empty set, extended to set theoretic specification of the magma, down to set of C, and it has to commute one way. Technically, it's a section in set categorical language, meaning it has to be the identity on set of C itself. So set of C goes to itself. So we're only mapping the remaining parts. We've already seen a morphism has to give an interpretation for every name. So this morphism is basically a tuple of, we call this M. It's a tuple of M of U of the proof of non-emptiness and of the operation. We have to give these three values to construct that morphism under the requirement that it's the identity on set of C, meaning we don't have to map the set of C. And of course, in mathematics, we usually don't actually give the proofs. We assume that the reader is taking care of those proofs on their head. So in the end, we have a magma in set theory as a pair of the universe and the operation. Or in the case of semi-groups, we would have, getting hard to draw now, this would be an individual semi-group consisting of the universe, the non-emptiness proof, the operation, and the proof of associativity. Now the integration of the Platonic and the formalist view I talked about yesterday tells us for every theory here, we get a set of sentences those are just all the expressions of type prop that we have over this theory magma. And we get a proof category of proofs over magma. That is basically the category of context and substituents. I haven't mentioned that yet. I have slides on that, but for every theory of LF, we can construct the category of context substitution. That's a very standard construction in type theory. Whenever we have a language, we can build a category of context and substitution. And that category very nicely doubled as what we could call a proof category if we talk to a Platonist. So we can say, yeah, we have a category here. The object are the judgments, meaning the things that could be true, and the arrows are. In particular, there's one operation here to here, which I call THM theorem, which maps every formula F to the context containing just one assumption that F is true. So that would be theorem F is equal to the context x colon that F, which is over context containing one requirement, there is a requirement that X be true. That way, we have our starting point for any proofs. Now we can prove this, we have to prove that. So this kind of talks just about the syntax. This category talks about all the proofs. This arrow relates the sentences to the proofs by giving us the judgment expressing the provability. Here it's trivial, but there are other logics where you need to prove more complicated things. In particular, think of, say, a resolution calculus where you have contradiction-based proofs, where you don't prove that F directly, but you have to prove something like starting with a clause containing the conjunctive knowledge form of F, we can get the empty clause. Then that would be a more complicated judgment. But in natural reduction-like calculus, it's very straightforward, just almost looks trivial. But technically, we have now separated the categorical construction of the sentences from the categorical proofs. And moreover, these are categorical themselves, are functorial themselves, so we have the same construction for the sentences of a semigroup and the same construction for the proofs over a semigroup. And now this morphs in here, because this I gives us functors over here, set of I and I, which give us sentence and proof translations along the morphisms in different languages. In addition to sentences and proofs, the one other thing we need is models. And that's what we get here now. We're saying for every one of these theories, in addition to the set of sentences and the category of proofs, we collect here the class of models by taking all the morphisms that go from here to this. And you see now here it matters which language we use to represent semantics. I could also take the push out going only until here, and then do models by going back into higher order logic. Then I would get models of, get magmas and semigroups in higher order logic. I could even start here. I could try to give morphisms from here straight back into full. Then I would get what you could call an internal model, where we give models of magma directly in the syntax. Now what happens is that these notions of model aren't the same. Generally speaking, the further to the right we go, the more models we have. Why is that? Well, the language becomes more expressive, becomes stronger. We can write more models. So we might not have any models in the internal language. And the stronger we make our semantic language, the more models we can construct. We can also say what it means to be true in a model. That's not very straightforward. We have the sentence F in the language of first order logic for a particular theory magma. It's an expression of type prop over this theory. We can map that expression over here. And we would have something like full sum of F. And then we can map this expression further along this model M. To have the interpretation of F in the model, which is then a truth value 0. The general definition then simply becomes translate that of F into a type that's now an expression over set of C. We've mapped it from the syntax to the semantics and then into the particular model. So we have set of C type, M of full sum of that of F. And if that is inhabited or not, so if this is inhabited, we can say that the formula F is true in the model M. If it's not inhabited, we say the formula F is false in the model M. Technically, it's a bit more complicated if the model isn't complete, but that's not. The push out also has a very nice property that if we have a model already built here, that model can also be moved over, and everything that's true or false in the model here stays true or false. So we can say it's basically the same model, just moves from the language of higher logic to the language of sense here. So as we go along to stronger and stronger languages in which we represent the semantics, we can write more and more models. Similarly, all the proofs get translated. Proofs are just expressions here. And we know morphisms preserve all expressions with typing. So all the proofs get translated as well. In particular, if f was already provable in the syntax, because it's a theorem to begin with, then f will be true in every model, because after translating the proof and translating it again, we definitely have a non-empty type. So we immediately have a notion of soundness. If these morphisms here translate also all the proof rules, we're guaranteed to be sound. Everything that's proven in the syntax is going to be true in every model. There could be more proofs though. Like, the stronger the language gets, the more things we have a chance of proving. So as we go along to the right, more things might be true. So then we have, if we go to the right to stronger and stronger languages, we acquire more proofs and more models. More proofs means more formulas are going to be true. And more models means we have more counterexamples, so more formulas can be refuted. So eventually those two meet. And that's the case when we say the semantics is complete. If every formula is either true and in every model, every formula is either true or false. And we say that the semantics is complete if it doesn't add any new theorems. So if this morphism here is conservative, if types that were already empty are still empty here. And then the model has to do the rest. So types that we have formulas here, but then these are provable and this provable. In the model, then we make the last commitments to reach a state where every formula is either provable or this. Normally, I would have shown that by switching back and forth between slides and Blackboard, but that's a bit complicated here. So I did the entire drawing. I hope you will remember that. And I'm switching to slide. Right. So this is a more formal presentation of what I just did. For every theory of our logic sigma, which is just an extension of the logic, we get a sort of sentences, a category of proofs. These proofs, we can define what the theorem of the contradiction is. And categorically, this gives us a functor that maps theories to sets. Another functor context, or you could call it proof. On the Blackboard, I call it PF for proofs, which gives us for every theory the category context. And the mapping THM I mentioned, that is then a natural transformation in the language of categories. So the interface is nice because this lets you unify the perspectives of formalists and Platonists. The Platonist is perfectly happy to take this as a definition of a logic. So the quadruple of a category of theories, a functor, another functor, and this natural transformation. And they're very interested then in studying all kinds of other categories that have the necessary properties. They think the formalists are maybe artificially limiting themselves to only those where all of these objects are induced by a singular left theory. But that's fine. And the other way around, the formalist thinks, well, the Platonists are studying way too many categories. The only ones that matter are the ones that come from here. But still, this is a nice interface to think about what the logic is. At least syntax and proof theory. For the models, then we need one other functor which maps the theories to the class of models. And we've also just seen how to construct that. If we have a logic translation and a prime, like I've shown you yesterday, remember it's basically just a morphism. We don't require prop to prop prime, but we do require that the debts go to debts, and then we can extract this term tau from the morphism, which we can think of as truth lifting, mapping the translations of propositions to propositions in the meta language, meaning the semantic language prime. This induces then platonically the theory P of sigma that translates the syntactic series by push out into the semantic language. We get a sentence translation just by applying the morphism, and we get translate proofs and disproofs. I've shown you examples of translations. So one I haven't shown is the one from type first order logic to high order logic. There we take high order logic by the set of Peter Andrews, which means equality is the only primitive connective. So basically we're starting just with type terms and equality, very close to lambda calculus. And then it turns out if you throw in Booleans and very mild assumptions, you can already define all the other connectives that we usually use, like conjunction, multiplication, and so on. So this is basically a logic translation from type first order logic to high order logic. And then if you formalize everything in the atlas, you realize that so really the only big difference is that here we also have Booleans and function types. But the logic is saying like, oh, the connectors and quantifiers are more or less the same. Showing you some more translations. And I've also shown you that some of these translations we had to create an additional theory of the target language to actually write the morphism, and that is the transition to semantics. This extra theory captures what it means to be a model. And if we have that, every translation induces sentence translation, a functor between context, mapping the context over, say, monoid to the context over the set theoretical language of monoids. And all the diagrams that arise commute in the intuitive way. And then the other way around, starting with the Platonist intuitions, going to the formalist perspective, what we have to do is we have to formalize everything that the Platonist assumes in the framework. I've already indicated that we can, for example, formalize a set theory in a relatively straightforward way. And alternatively, we could do calculus of constructions or any programming language, whatever we want to assume to be the meta language in which the semantics is expressed. We just formalize that in the logical framework. We translate into it, and we have semantics. And we can define what it means to be a model theory in general and to be an individual model. So all of these slides are just recapping what I sketched on the board. Also said already, already. And when it comes to the formalization of models as morphisms, there's one subtlety. So normally in a Platonic model, every formula must be true or false. We usually assume that the model is something that exists in reality, and in reality, every formula is true or false. Turns out this often requires our formalizations of the Platonic environment to be extremely strong. So you know this theorem, the incompleteness theorem by Gödel, that if we formalize the natural numbers in first order logic, it's not actually strong enough to prove or disprove every formula about the natural number. So this effect we have all the time. So whenever we represent a model in the logical framework, there are certain dangers that we can't manage to prove everything. So for example, I could write a model for just propositional logic with a single propositional variable p, and I map p in set theory to, say, the axiom of choice. Then if my semantic foundation is set f, then in this model, I don't know if p is true or false, because the axiom of choice can't be proved or disproved in set f. So if I write a model in which I interpret the syntactic symbols I have using sufficiently complicated constructions in semantics, I may be able to reach statements where the semantics can't make the formula true or false. And this never ends. If I go to set of C, I can just map something to the continuum hypothesis, and again, the set of C can't prove what this is. So there's a bit of a philosophical issue here. What do we actually call a model? The Platonist assumes the model actually has functions that go into the set 0, 1. So we somehow write the function as an object, and then it's clear whether the formulas are true or false. The propositional variable can't go to the continuum hypothesis. It can only go to 0 to 1. But formalists can write a morphism mapping p to any expression of the truth value type. And then maybe that's an expression that doesn't reduce to 0 or 1. And then you can fight over whether that counts as a model. What it has to do with normalization. Are you interpreting the syntax as values in the semantics, or are you allowed to interpret it as arbitrary expressions? In which case, it would be the semantics' job to reduce those to values. And in that case, maybe the semantics isn't able to reduce. But we can always keep the model as it is and just strengthen the semantic language. For example, if we insist that the interpretation of our propositional variable should be the axiom of choice, and set f just doesn't commit to what the truth value is, but we could have the same model in set of C, and then we could reduce the semantics of p to true. So because these models are preserved when we go to stronger semantic languages, that's okay. We can leave our models with some formulas not reducing the semantics. And if we absolutely have to be able to reduce them, we just have to use stronger semantic languages in which we have to make a commitment how these formulas reduce. So one of the most important changes in the way how I see logic that I've then acquired over the years is that I don't really strictly distinguish syntax and semantics. And I don't distinguish translations from semantics. There's just a continuum. For example, from modal logic, we can translate to first order logic. First order logic, we can translate to higher order logic. Higher logic, we can translate to set of C. And it doesn't really matter, like there's no point along this spectrum where we can say C as syntax stops and semantics starts. It's all just translations between different languages. One might already say, well, this is the semantics of modal logics. And first order logic just serves as a fragment of set of C, like the weakest fragment strong enough to express the semantics. Or one might argue, no, this is a logic translation going from order logic to first order logic. So the morphism itself doesn't require a commitment to whether we see it as a translation or as semantics. Most people will say, well, if you go to the C, it's semantics, but actually, set of C works perfectly fine as a formal system. We can think of a set of C as a logic. It's a relatively expressive logic, sure, but it's a logic nonetheless. We can write theories over the C, like what it means to be a magma or a semi-group. We can have formulas about them. They're very expressive formulas. Don't have a complete calculus for that logic anymore, but still perfectly fine as a logic. So it's perfectly fine to think of this as a logic translation. And so I see it much more as a continuum now. We can go further to the right in this continuum to get increasingly strong languages. In those stronger languages, we'll be able to settle more questions because we'll have truth values assigned to more things. We'll have more proofs to prove things. We'll have more models to refute things. But everything we do further to the left remains valid. So we usually work as far to the left as we can. And this diagram, by the way, is misleading. Then when I say continuum or spectrum, it's also misleading. This is by no means linear. This is a very complicated graph. Like, it's not just one series of translations. We have all kinds of translations, including cycles and branches in this diagram. There are 2 points, though, that are worth thinking of especially. We have something called the initial semantics and the final semantics. The initial semantics would be the special case where I use the identity morphism here. So I would say, well, I have the identity translation from a logic to itself. In principle, that's a morphism, just like all the others. We can call that a logic translation. We can call that our semantics. And actually, yeah, that's exactly what's happening when people do initial semantics. Or when you think about Haber models, what do? You take a model whose elements are the terms over the syntax. So you're using the syntax itself as your model. So that exactly corresponds to taking the identity morphism of the syntax as the semantics.
Is that the same as a standard model?
No. A standard model depends on the context in which you use the word. Usually means that there's some kind of intended interpretation. Like the standard model of the natural numbers is the Platonic natural numbers. So in these models, typically we have the effect that since we have started with the syntax and the syntax proves only some of the formulas, we don't really have that every formula is either true or false. We have 3 groups of formulas, the provable ones, the disprovable ones, and the rest. So we often have to do some completion operations to actually make models where everything is either true or false. In Prolog, that's negation by failure. If you can't prove an anthem, you assume it's false. But still, it's essentially using the initial morphism necessary. And then dually, we can think about, okay, what will be the endpoint? So if we keep using stronger and stronger languages here, can we converge at some point? And well, we can somehow maybe. I haven't been able to express it as a morphism yet. Because, yeah, whatever language you think of here, it's always one more that you can translate into. But there is a certain natural limit to those constructions. If you think of some kind of logic in which every theory is mapped to its set of theorems, and you think of the maximally consistent sets of sentences as the models. That is, as I said, I can't represent it in this way, but it has exactly the properties of a limit. No matter what you do, you can always translate into this one. So this is kind of the last one, because everything else can be translated into it. The final object in the sense of capital, a terminal object. So this is kind of a challenge how to actually capture this in logical framework. referring to the idea that, okay, a model really is just a set of samples. Interestingly, those are pretty boring models, and we lose all this structure of the data that we want to talk about in our models, but that's the natural endpoint of this. And eventually we have the overall definition of what a logic is. Theory as a distinguished property. Proof system, we extend the syntax as proof rules. We have a theory F for the mathematical foundation, theory M representing what a model means, and the morphism for the semantics, the morphism I for the semantic typing the syntax into the foundation. And in the way I've shown before, that then gives us categorical notions of what are the sentences, what are the proofs, what are the models, what does it mean to be true in a model, and so on. And we can define soundness and completeness. The semantics is sound if the translation of the syntax to the semantics can be extended to also translate the proof roots. That's usually relatively easy. Just extend the morphism by mapping all the proof roots. Most of the time it's a student's exercise. And the other way around, the semantics here is complete if the morphism is conservative. There's a couple of different ways to define that. One way is to say it has to preserve consistency, meaning if we apply the morphism to map theories from the syntax to the semantics, the consistent ones have to go to consistent ones. Or we can say that the empty types must go to empty types. Preserve emptiness of types. So if that F was empty in the syntax, it has to remain empty after the translation. Then we can call it semantics complete. Conservativity, we can also think of as if a type is inhabited in the codomain, if the translation of a type is inhabited in the codomain, then it must have been inhabited in the domain. And that's exactly how in textbooks we usually define completeness. If we can go to the semantics and prove it there, then we must have already had a proof in the syntax. So we gain some very nice definitions of logic and sounds and completeness. And completeness, unfortunately, I have not been able to figure out a way how the logical framework can help with proving completeness. So it helps to define what completeness is, but I haven't really come up with good proof. Arguably, we would need some kind of meta-theorem prover where we can talk about the framework now, where we can formalize the statement empty types go to empty types. And then we might be able to formalize the typical completeness proofs in such a meta-LF. Okay, so that concludes the logical framework definition that merges formalism and Platonism. And I have already shown you the logic atlas with logics and translations written in that framework. What I have planned for the remainder of the lecture is a couple of selected problems and current work limitations of the approach. But before I start there, are there any questions? Okay. So I think I have 3 loosely connected sections talking about certain open challenges. So the first one is, I've said that a logic translation is just a morphism. And I've also told you that morphisms have extremely nice properties. They preserve all judgments, and I think what I haven't mentioned is they also commute with substitution. What that means is I have an expression in some context, and I apply a substitution, into some other context. And I can apply a morphism to get the expression in a translated context. And then I can go here by now applying the translated substitution. So M of E applies the translated substitution. And that is the same as if I take the substitution first and then map the whole thing. So first substitution, then morphism is the same as first morphism, then substitution. Intuitively, that's clear. The morphism maps the global symbols. The substitution maps the variables. Both are doing it by induction. They don't interfere. So it kind of makes sense that that would commute. This is what's usually called the substitution theorem. In textbook, it's usually phrased in a setting where M is a model. But we can prove it much more generally for an arbitrary morphism. And then since we have represented models as morphisms, we automatically get it for model. So this is a very powerful property. It basically gives us things like separate compilation. What happens in separate compilation? We have two modules and we compile them individually, where compiling would be an application of a morphism. And then afterwards, we can link the compiled binaries together. That's exactly what's happening here. The linking is applying the substitution to make the two modules work together. Compiling is a morphism application. And the commutativity says that that's exactly working out. Meaning you can translate your theories individually and then link the results. Or you link the series first and then translate the entire program. So this is the path that we first link, then translate. We first translate the components and then link them. So basically, the commutation with substitution is given to us by morphisms, and that gives us all of the important modularity properties, in particular things like separate compilation. So the morphisms are really, really good, but then the flip side of that is they're quite restrictive. And there are many translations that simply don't have those properties. And then naturally, we cannot represent those as morphisms. And it happens a lot in practice that we have logic translations which we just can't write as theory morphisms. And well, roughly speaking, whenever it's non-compositional, then we can't do it as a normal morphism. So I just said compiling can be seen as a special case of morphism application, but if we have an optimizing compiler that goes in and does all kinds of tricks, it's usually non-compositional. In fact, that's a defining feature of an optimizing compiler, that it does non-compositional things in order to get the simpler binary. Usually you do special case treatments. You don't translate a language feature the same way all the time. Instead, you look into the arguments. If the arguments are particularly simple, you translate it differently. Think of loop unrolling. If the loop goes from 1 to 3, you don't translate it to the loop in the target language. Instead, you just duplicate the body of the loop 3 times. That's the non-composition. So generally, whenever there are these special case treatments where we inspect the arguments and do different things depending on what kind of arguments we have, whenever there are nested inductions, like we do an induction of the syntax, that's what the morphism does. But if any of those cases needs another induction to define the case, then we're typically non-compositional. Whenever we do a two-pass thing where we first go through the entire library that we want to translate and collect all the occurrences of a feature, and then do something to that, then we're non-compositional. A typical example would be the elimination of subtyping. What we can do is we can go through the entire library that we're translating, find every place where the type checker has used subtyping and insert then a special casting function for that occasion. Then we can go to a language without subtyping. We just have to prefix the translation with a humongous list of casting functions, one for every subtyping relation that ever occurred in the library. So those translations are not compositional. They break all kinds of modularity conditions that we would like to have, but they are nonetheless real and important. And it's a bit of an open problem what we do with those. Here are some typical things that lead to problems. So the PVS subtyping is undecidable. If you want to translate PVS to any language that has decidable subtyping or no subtyping at all, you're going to have to do something non-compositional. MISA has soft types. If you want to translate soft types to a hard type language, you're going to have to do something weird and non-compositional. If you have partial functions and you want to translate to a language that doesn't have it, only has total functions, maybe you can do it compositionally. You could say, oh, okay, partial functions are made to become total functions from A to option B. That could work. But you might then get relatively ugly results. That's another thing. In practical translations, you want to produce not just some translation, but an idiomatic translation. So all these casting functions that you need to eliminate subtyping typically gets you translations that really look ugly. So you can take the PVS library, translate it to, say, Coq, but the resulting library you're going to get is probably one that no Coq user wants to use, because if you had to do it in Coq, you would do it differently. You wouldn't have all these casting functions. You would maybe choose an entirely different way to formalize in the first place. So you cannot, in practice, use the translation, even if someone provides them. Another nice example I had in my own work, we were translating from a nice functional programming language where we could do software verification to Java, and also monetic work that was very good for software verification just wasn't right in Java. In Java, we wanted exceptions running, rather than having some kind of error monads. So translating error monads to exceptions throwing completely but it completely changes the structure of your syntax trees. So it's also non-compositional, but it's necessary to get results that actually look good. So you have to think about what kind of translation you actually, like what you want to use your translation for. If you only ever needed to verify the results, maybe it's okay to have ugly looking translation. But if you only want to have the translation as a witness to prove that it's possible to translate, then it also doesn't matter what you get. But if you want to then later use the translation to move the library of the source logic into the target logic, and if you then want to actually use the translated library in the target logic, you better produce something that's idiomatic. And so that may mean that even if a compositional translation is available, you want to instead do a non-compositional one that produces better looking. And unfortunately, this happens pretty much everywhere. Take any two-proof assistance, try to translate from one to the other. It's basically impossible to do it compositionally unless the source system is whole light. Whole light is deliberately as simple as possible, and because of that, you can translate it compositionally into other systems. And that has been done. But every other system has its own idiosyncrasies and its bedding. Not hopeless, but it's not something you can give it to a student and expect to be done in a couple of months. It's more like a postdoc working for a year. or you cut corners and you don't translate the entire stuff. You could just say, okay, anything that uses extensible records of PDS, I just skip it in the translation. That can work. But then you have partial. So partiality is another way to get around these problems. So one particular challenge problem that I've been looking at recently, actually working with Thomas on that, on the deductive side, is to go from hard typing to soft typing. That's the easy direction because soft typing is more expressive. We can do everything we can do with hard typing, we can also do with soft typing. And intuitively, the translation is straightforward. Just everything that's a TMA becomes just term. And we just erase the typing information from the terms. And then additionally, of course, we have to prove that the translation of a term is typed softly by the translation of the type in the target language, if it was typed that way in the source language. So proofs can be done. That's also relatively well known. But now, how do we represent the whole thing in the framework? In particular, this big proof requires one long induction on terms and types. And it turns out one way to do this proof, one way to structure the induction is that you get basically a logical relation. I'm not going to go into details of that. There's a paper if you're interested. The rough idea is morphisms give us a way to have nicely behaved inductive functions between theories. Logical relations give us nicely behaved inductive proofs about the syntax. And then we can actually come up with a logical relation that captures exactly the proof that typing is preserved. But that translation doesn't work so well for the proof rules. So we're still not good enough to bundle everything up in a way that we could translate the entire hard-typed language into soft type. Another option is to use sigma types. So instead of erasing the A completely, we just erase it and immediately pair it with the appropriate proof. So instead of having one translation that erases the types and a separate induction to recover the typing information at the levels of proof, we keep the type information around, pair it up with a translated term. So then we get proof carrying terms. Even though the translations of all the terms have proofs inside of them. So we're going to need to change the target language. I mentioned that briefly on, I think, Tuesday, that if we have proof carrying terms, we have to watch out. Some features have to be formalized differently. So for example, we need dependent connectives, which is basically saying, if I have a formula F, I want to prove that an implication is a proposition. I normally do this. F must be a proposition, and G must be a proposition. With dependent connectives, I am already assuming F to be true when I'm proving that G is a proposition. Because this assumption of F could come in handy when showing that G is F. So then that gives us dependent connectives where we need to assume an assumption here that F is well formed, that we might use that in the proposition G. So formalizing dependent connectives is straightforward enough. It's just we technically don't have propositional logic anymore. We have a variant of propositional logic with proof carrying terms and dependent connectives. So if we wanted to translate soft typed first order logic, no, hard typed first order logic to soft typed first order logic, doesn't work with this option. But we could translate hard typed first order logic to soft typed first order logic with dependent connectives. So could say, okay, you know you're cheating, you're changing the target language. But another way you could say, okay, we're just realizing that the target language was the wrong one all along and fixing the translation. And this translation is important because that's also at the heart of doing semantics, because set theory is untyped. Or rather, it's soft-typed via the elementhood predicate. So every time we formalize semantics, we will end up essentially with these morphisms that have to handle the fact that we're translating something that's hard-typed into something that's soft. So figuring out how to do this correctly is like a key missing step to get the semantics of languages formalized. Time. I might briefly show you happening there. Formalization of set theory. So that's a theory of first order logic, but now with dependent connectives and also with a description operator. The sets are just the untyped universe of first order logic, and then we have the in predicate to get to the usual notions of set theory. And then set theory usually starts with some axioms, like the power set axiom, which says for every set A, there is a set Z, such that Z is a power set of A. And then using the description operator, we can actually turn that into an operation which maps sets to their power sets. So the set theory formalization in the atlas splits things up. We first have abstract descriptions of the feature, like this is the abstract description of what it means to have power sets as a language feature. And then there is the axiom that states the existence of power sets. And then there's a morphism that says, once we have this axiom, we can actually realize the feature of power. We do that for 10 or so different axioms that are used in set theory. And then those can all be collected into say set of C. To get to typed reasoning, we make a conservative extension of set theory. Conservative, but with new primitives, which give us for every predicate on sets, the type of elements of that predicate. So it's like lifting the soft typing of set theory. In set theory, we use soft typing, and we usually consider the predicates as the types. And in particular, every set induces the type by taking the predicate of element in that set. And we're lifting all of these to the type level of LF so that we can then have a morphism from any hard type system that maps types to sets so that we can map terms to elements of these sets. And then these constructions are basically saying, well, we have sigma types, except specialized to this constructor. So this is a pairing operation. If you ever have an X and a proof of P of X, then we get an element of P. If we have an element of P, we can get the underlying set back. And if we have an element of P, we can get the proof that the underlying set actually satisfies the predicate. There's an axiomatization of sigma types. An axiomatization of precisely these sigma types here, which we can then use as a target for representing hard type languages in set theory. Okay. Any questions on this issue? Then otherwise I will switch to another issue that's worth mentioning. That's declaration patterns. So I've so far always said that the theories of a logic L are the extensions sigma of L. So we start with our formulation of first order logic, and say all the extensions, those are the theories of first order logic. But actually, we only want some extensions. Typically for first order logic, we want these. Untyped first order logic allows exactly 3 kinds of declarations in the extensions. Function symbols, taking n arguments, returning a result. Predicate symbols, taking n arguments, returning a proposition. And axioms. The first order theory shouldn't declare anything other than these 3. So when we're saying that the theory of first order logic is an extension of L, we're actually producing too many, way too many actually. But every individual theory that we formalize, of course, conforms to these requirements. So in practice, it doesn't matter that much that we can't rule out the others. But it would be more practical to have a version of LF where we can declare these patterns or templates so that when someone is writing a particular theory, the system can say, hey, you're doing something that's not allowed in first order logic. Are you sure? If we then want to build tool support, we could leverage that. We could write special tactics that are only sound if only these kind of things are declared. We could write tactics that check at all the function symbols, build all the terms, and then do kind of unification optimization or equivalence closure or something. These kind of things only work if you have a guarantee what kind of declarations the user has added in their theory. So it would be good if the framework could give us some guarantees what kind of declarations to expect. So far, there is no good system that does it. We specified one, and we also implemented it as a part of MMT. MMT has most of the capability, actually, but turns out the patterns that we need are often quite annoying. Already here, the ... tells you that this is going to be problematic. If you want a formal syntax in which you can write down this pattern, you need to somehow talk about natural numbers or about sequences so that you can say any length here is allowed. So suddenly you need natural numbers already to define what first order logic is, which is kind of awkward. But it works very well for some languages. The best case is higher order logic. For higher order logic, we can declare new base types. Typed constants, CTMA, for some type A. So I'm using some ad hoc syntax to say, these are the patterns of the declarations that can occur, and these are the parameters that the patterns may take. So we can declare an axiom, P that has for any F. Oh, this has to be a prop, sorry, it's a typo. And we can declare a typed constant, CTMA, for any PA, or a new base type. Now we can actually be quite specific. Sometimes logics actually only differ in their patterns. So for example, textbook higher logic might be defined with these patterns, but it doesn't have to be. The church's higher logic didn't have this. In church's higher logic, there was one base type of individuals, and that was it. Well, plus the Booleans. The user wasn't allowed to declare additional base types. So through the patterns, we can have these fine granular distinctions what the logic actually is. And pool-based proof assistants typically say, well, yeah, you can have these, but you always have to define stuff. Like you're not allowed to have new primitives in the language. It's based on the idea that you give the axioms once, and then the user just does definitional extensions. So in proof assistants, you would have patterns where these things are allowed, but only if they're defined. And then in higher order logic, typically we have this complex pattern, which is the subtype definition principle, which is the one non-definitional extension, where you give a type, a predicate on that type, and we're getting back a new base type, which is axiomatized to be isomorphic to the subtype of A given by this predicate. So if you look at like Hollein or Isabel Hole, deep down in the kernel, that is the fundamental principle that the code runs through when it creates new languages and new theories. all the other high-level stuff like inductive types, recursive function, and so on, they're all defined ultimately in terms of this. So the user documentation doesn't even mention this anymore. It focuses on end users, and it only shows the high-level constructions you can do. But all of those high-level constructions are elaborated, and ultimately, whenever you create new types, they go into the subtype principle, and in particular the ups and Rabe. You've maybe seen this in some papers before. You encounter these in higher logic papers again and again. So this is a nice success story where the patterns of higher logic can be written down very nicely in a relatively straightforward declarative language. But for other patterns, it didn't work so well. So we have good theory on these patterns. We have an implementation, but yeah, for first logic, we will need something like this. For any natural number, we can declare a function symbol f that has n repetitions of terms in the inputs and returns a term. Similarly, if you want to state patterns for polymorphism, those can be tricky. I'm going to say, we have an arbitrary list of free type variables and then a typed constants. So catching these, even though it's straightforward what we have to do, it's difficult to come up with a logical framework mechanism where users could, as part of the definition of a logic, say what the patterns are. But we kind of stopped working on that because in practice it doesn't matter that much, as long as every single theory we actually work with happens to conform to the pattern. But if we have these patterns, one cool thing we would be able to do is to leverage them in translations. So if we're going back to the double negation translation from classical to intuitionistic logic, I've shown you that I inserted the double negation at the top level. And occasionally we need a double negation in the middle. Also, that's easy to do in a morphism, because it usually happens in front of some connective. So in the case for translating that connective, we just stick in the double negation. But then what we usually also need is we have to double negate all the atoms. And that's something that logical frameworks sometimes gloss over. When we formalize a logic in a logical framework, we're usually formalizing the variant where there are no atoms at all. Like the formalization of propositional logic, we have propositions, connectives, true and false, and that's it. We don't say anything about, we have P, Q, R as propositional variables. That's expected to be done by the user later as an extension of the language. So the logical framework doesn't really do anything beyond formalizing the empty theory and allowing the user to extend it. So when we're translating, we don't really have a good handle on what kind of atoms the user may have declared. And then we're not able to do anything with them. So in particular, for the double negation translation, we have no point in the formalization where we could stick this rule that we also double negate all the atoms. If we had declaration patterns, we could do it. The pattern would maybe look something like this. Let's give it a name, PV for propositional variables. It's just a P colon prop. Everything that happens in propositional logic. And then we could say, well, we translated somehow by mapping the P to not P. This is a made-up ad hoc syntax. I've never implemented something like that. But that would be a way how we could leverage the patterns to do translations where we have to do something to the atoms as well, which does happen frequently. So any questions on that? So even though logical frameworks are good at telling us what the propositions are, what the proofs are, what the models are, when it comes to restricting what the theories may declare, we still have a gap in the design of logical frameworks. And that gap is particularly noticeable in translations where we might want to translate different declarations differently. And we might want to say this declaration is only applicable if the user has only made certain declarations. Okay. And finally, a little bit of outlook to what's happening with real-world systems. So I said that it's difficult to do logic translations between real-world systems. In fact, it's difficult to even formalize the real-world system in the first place. By real-world systems, I mean things like PVS, Isabel Lean, and so on. And now, okay. So the basic idea of the naive approach, which you'll see again and again, done by people who don't have 15 years of practice doing it, is to think, oh, we just translate one logic to another, and then we can move over the entire library. And I've already hinted at that doesn't work. We typically get something entirely different in the target language. Even if we have a logic translation, the translation of the library is usually useless. So I'm going to give you some examples. If we want to do division, there's all kinds of different ways to represent the fact that division is a partial function. Every library is forced to pick one of these, or yet another way. If you have a library that picks one of these, and a second library that does a different thing, you typically won't get a logic translation that gives you a library translation where the division of the source language goes to the division of the target language. So you're going to end up with some other operation in the target logic, which behaves kind of like division, but which is not tied to the division that was already present in the target system. Subtyping is a big deal. Every library has to make choices already for the numbers, where and how they use subtyping. They will typically make different choices. So if you're trying to translate, already the translation of numbers will be a mess, because the way how the numbers are defined in one library just won't match up nicely with a different library. The algebraic hierarchy is a similarly elementary example where systems usually totally disagree on what exactly the inheritance hierarchy between the different theories is. Not to mention different ways of writing theories in the first place. So in the end, you get a kind of weird conclusion that logic translations are neither sufficient nor necessary. And they're not sufficient. If we have a logic translation, we can translate the library, but it doesn't give us what we want. But interestingly, they're also not necessary. In a way, they're not even the thing we should be worrying about. So what's much more important is to translate between libraries. And a translation from, say, the Isabel library to Lean or whatever might be able to completely ignore the fact that those are different logics. Coming up with a logic translation from Isabel to Lean is what most people would start, like what most people would see as a natural first step. But actually, you can skip that. I mean, obviously, you need to do something with the Isabel logic, but the much more important question is translate the real numbers of Isabel to the real numbers of Lean. So you really want to start back from, start with the library and translate only as much of the logic as you have to. There's no need to first have a complete translation of the logic. And then you realize that this library translation is actually anyway 95% of the work. So the logic translation, to the extent that you need it, is something you can do along the way. So this alignment, this gets us to alignments. Basically, alignment is a pair of symbols in two libraries that formalize the same concept, like the wheels of Isabel and the wheels of me. And you really need to think about, okay, which symbols are aligned with each other? And how do I get from one to the other? Because typically they're going to be aligned, but they will have different types, like division being formalized differently in the two libraries. You have to think about how can you actually translate between aligned symbols, but that have different types in a way that can't be fixed by alignment. You're going to have lots of special case treatment for the various symbols. And maybe the best is to just collect the pairs of alignments, translate all the expressions by naively changing the real numbers of Isabel to the reals of Nien. Being completely aware that the result is probably an ill-typed expression in the target language. And then maybe have separate tools that fix the typing. Maybe there are some AI tools that can take a kind of well-typed Lean term and make it well-typed if they've been trained on MathLab. Maybe there are some systems where you can just infer the missing proofs, like say you have a division that doesn't carry the proof that the second argument is non-zero, and your target language has division where the proof is carried. All you have to do is recreate a proof in the target system. So you translate, you run a theorem prover, maybe you can find the missing term. So these kind of inference mechanisms, or maybe some machine learning, or just shake the term long enough until it becomes well-typed, may work. And the same applies to proofs. Probably it's not worth translating the entire proof calculus of Isabel with a proof calculus of Nien. Instead, you want to translate at the high level. If Isabel is applying an induction tactic, you want to call the induction tactic in Nien. Maybe your translation of the induction hypothesis is ill-typed in Nien, but maybe that can still work out if you have a tactic that uses the translated induction hypothesis to guess what the Lean induction hypothesis should be, then maybe the Lean induction tactic will be able to fill in. So translating at the high level, the general proof sketch is much more important. Isabel calls the auto tactic, maybe in Lean you also want to call the auto tactic. These kind of things. So I think that's going to be much more promising to actually integrate libraries. These kind of tasks are extremely difficult though, and extremely expensive. So very, very little is happening in that direction. The deductive people are doing translations into deductive at least, but there they often eliminate features in order to make everything fit into deductive. And those high-level features are gone, so you can't translate induction of one system to induction of the other system because you've eliminated induction when you went to deductive. A couple other people are trying occasionally to translate one library to another system, but generally this is a wide open problem, how to make the logic libraries interoperable. And it's also an open problem if we even need that, or if we should just pick one winner and ditch all the other libraries. And most of the people work on individual libraries, and they're voting for the second approach, except they're voting that their library should be the winner. We should ditch the others. There's very few people working on the top. We'll see. Maybe the market will develop in a way that indeed only one or two winners will remain. Mathlib is now a strong contender on lean. But yeah, that's all. And well, I'm 2 minutes over time, but that's pretty much all I wanted to say. Any questions? Yeah.
I mean, just about the thing that you just said, it's very basic question, like general question about your opinion. What are you saying that there is only going to be one winner?
No, I'm not saying there is. I'm saying it's a possible scenario. And it's unclear what will happen. Are we going to be stuck with 5 to 10 incompatible systems? Are we going to have a good interoperability framework? Or are we going to have like 2 systems that be? So no one knows. Well, it's going to be a couple of decades to find out. It's also difficult to, it's not only difficult to bet any of these, it's also difficult to choose which one would be the best. Having one library that everybody uses would release humongous synergies. We could formalize a lot more, but then we might also get stale because we don't try anything new anymore. Having multiple different libraries competing with each other might give us better utilization of evolution.
Maybe it's the most likely, like for example, if we compare it to programming languages, they have been just spreading more.
Exactly, we have the same problem in programming languages, and they're just problem there. No, the benefit there is programming languages are so widely used. Every single language has enough customers to survive on its own. Occasionally languages die and others are born, but there's a dozen or so successful programming languages, and they all have enough funding sources to just continue. And we just duplicate all the libraries. Whatever library we need, we just write it 12 times in 12 different programming languages, and that's okay, there's enough people to do it. With formalization, it's different because we don't have as many people and not as much funding. So it is a serious concern that we are currently formalizing everything multiple times over in different systems. I would have said the most likely scenario is that everything continues the way it is. But over the last couple of years, Mathlib has become so strong and has become so good into making mathematicians believe that it's the only option, that at least in the area of formalized math, it has a serious chance of winning. In the area of software verification, we're probably going to go the way of programming languages. That means you have multiple competing systems that are all strong enough to survive permanently. Simply because software verification is going to have an increasing amount of funding in the future because it's becoming more and more important. So those systems won't die out, but the focus might shift more and more towards software verification and away from math, because that's where the funding is. Any other question?
Another question used. I think in a sense, for the programming languages, we already have interoperability in some sense. I mean,
that's another aspect. We have kind of assembler or binary interoperability. And one big difference, especially in math or in logic in general, is that we would also like to have interoperability at the level of high-level data structures. If you have, I don't know, a polynomial constructed in one system, you would really like to have a polynomial in the target system. You have some subgroup object or whatever, you want to get the corresponding subgroup object. That's something that you usually can't do well with programming. The other solution is just, okay, in the worst case, serialize everything into XML or JSON, and then reparse it on the other side. I mean, that would be awesome if we had that for proof assistance, but we're even far away from that. Yes, Deducti is trying to be like the assembly language, giving some kind of like low-level compatibility. You do half the proof in one system, the other half in a different system, translate everything to Deducti, and then there you can link it together. It can work. but so far it has mostly been used for proof checking. It's very hard to do it in the proof development phase already, so most people just have kept using single individual systems without utilizing it properly. There was one more question, I think. Yeah.
Would it possibly make sense to take on the alignment problem in the same system after translating with the logic approach?
Yes, it could. And it's probably best to do some kind of combination. Parts of the logic that you can translate easily, like simple function types, you have in most systems, so of course those should just be translated. Systems differ in how they do inductive types, but the vast majority of actually used inductive types are very simple and they're all supported by all of the systems. So at least those inductive types you can just translate over. And then you're gonna have some mixture in the end of something where some symbols have already been replaced with the analog from the target system, and some have become new symbols introduced in the target system that we would rather replace with whatever the like. Whether or not you do it in 2 steps, first translate then align, or in one big step, probably the second approach is better. But if you don't know how to align, you might also produce ill type something suboptimal and then say, hey, you target system library maintainers, here's a dump of the source system library. I've already translated what I can. Pick what you need and align them. And maybe eventually we'll have enough people that doesn't need automation. They can just take 10 or 20 lean enthusiasts and they go over the Isabel library and port the relevant parts manually if they get enough support so that half the work is already done. Like if you throw an ill type export of the Isabel library into lean maslib, might be a good chance that enough enthusiasts just say, oh yeah, this file I know and I'm interested in it, I'm just going to port it as an exercise and then it gets merged with the maslib. So maybe that kind of combined approach of logic translation, machine learning based fixing, and human fixing could win out. But currently we're not even starting because nobody's doing the initial translations. Other questions? Then that concludes the logic design lectures and the break.